Hello, my name is Jiwon Park, a master student at Korea University, attending the 2023 Livable Cities Conference organized by AMPS. My presentation is titled Analysis of Cooling Energy Saving of Chiller Staging Strategy in a Medium-Sized Office Building. I hoped to network and discuss research face to face with other participants in New York, but due to various circumstances, I regretfully have to participate through a pre recorded video. First of all, our research, which I will talk about today, focuses on the engineering approach to understanding how buildings should be operated to create sustainable cities. As you all know, there is a increasing global interest in climate change, and everyone agrees that we need to build carbon neutral cities. To achieve a carbon neutral city, we need to reduce energy consumption in cities while producing renewable energy. Buildings account for approximately 40% of global energy consumption, and in densely populated urban areas, the energy consumption due to buildings is even higher. Therefore, reducing building energy consumption is crucial for creating a carbon neutral city. This research aims to optimize the energy usage of the HVAC system in buildings to reduce building energy consumption. HVAC design is typically determined during the building design phase, and the HVAC system chosen at this stage determines the building's energy performance for decades. The table below is the equipment life expectancy chart provided by American Society of Heating, Refrigerating, and Air Conditioning Engineers. According to the chart, the life expectancy of a chiller is around 20 years. Based on this table, the performance of the chiller determined during the design phase will determine the cooling energy efficiency of the building for 20 years. Building's heating and cooling load is determined by a simple thermodynamic equation involving the mass of indoor air and the temperature difference between indoor and outdoor air. Assuming that the indoor air is maintained at the set point temperature, the outside air temperature has a crucial impact on the indoor cooling load. Building heating and cooling energy refers to the amount of energy required to meet the heating and cooling load of a building. It is proportional to the heating and cooling load, but also heavily depends on the efficiency of the equipment. On the other hand, equipment efficiency is proportional to the part load ratio (PLL), which represents the ratio of the actual load to the equipment's capacity. For boilers used in heating, they operate at high efficiency except at very low PLL. However, for chillers used in cooling, the variation in coefficient of performance (COP) based on PLL is significant. At low PLL, the chiller operates with very low COP, resulting in high energy consumption even with a lower cooling load. This research focuses on the Incheon region in Korea as the building location. Korea has categorized as a 4A arid climate zone, which has cold and dry winters and hot and humid summers. Usually, the capacity of heating and cooling equipment is determined based on the coldest and hottest days. So during the transitional seasons, the load is significantly lower than on the coldest or hottest days, resulting in the equipment operating at low PLL and consuming more energy. Therefore, our goal was to find a way to efficiently operate chillers that experience significant efficiency changes based on PLL even during transitional seasons. We explored the advantages of operating a single building with multiple chillers, where all chillers are turned on during the hottest days, and only one chiller is turned on during days with minimal load, and the number of operating chillers can be adjusted as needed. Additionally, we aim to find the optimal algorithm for distributing the load among the chillers. First, the uniform algorithm evenly distributes the load among all chillers once the minimum PLL is reached. Second, the sequential algorithm utilizes the fuel capacity of each chiller and turned on the next chiller. Third, the sequential uniform PLL algorithm distributes the load evenly among the turned-on chillers while utilizing the fuel capacity of each chillers. Fourth, the optimal algorithm turns on the next chiller once the optimal PLL of 90% for each chiller is reached. In this research, we validate the effects of dividing the cooling load among multiple chillers using these four algorithms. This research utilized the building energy simulation software, Energy Plus, developed by the Department of Energy to calculate the building's thermal load. Microsoft Excel was used to distribute the load to each chillers and calculate efficiency and energy consumption. For the chillers, the Department of Energy's reference chiller was assumed, and the efficiency, energy consumption, and other parameters based on PLL were calculated using the specific chiller's performance curve. The building in this study is based on the reference building model developed by the Department of Energy. These reference building models cover 75% of the commercial building floor area in the United States, including commercial buildings and mid to high rise residential buildings across all U.S. climate zones. The specific building used in this study is a medium-sized office building based on in Baltimore, which falls under the 4A climate zone similar to the target region. The physical characteristic of this model are as follows. The building is divided into 15 zones with 5 zones per floor and 3 floors. The window to wall ratio is approximately 33%. The following are the research results. Case 1 to 10 represent the number of chillers present in the building. For example, case 4 indicates that 4 chillers are responsible for the building's cooling load, while case 6 means that 6 chillers handle the cooling load. The chart below represents the average coefficient of performance COP, and the conventional case with only one chiller is labeled as case 1. Case 1 has an average COP of approximately 3.0, but as the number of chillers increases in all algorithms, the average COP gradually increases. Additionally, we found that the sequential uniform PLL algorithm yielded the highest average COP in all cases. When examining the annual cooling load and cooling energy consumption for each case, it is observed that as the number of chillers increased in all algorithms, the cooling energy consumption decreased. It is also evident that the sequential uniform PLL algorithm resulted in the lowest energy consumption among all cases. The following is an analysis of energy savings compared to case 1. By using 2 chillers instead of 1, there was an annual energy savings of over 20% in cooling energy consumption. Additionally, as the number of chillers increased in all algorithms, the energy savings in cooling also increased gradually. As observed in the graph, the sequential uniform parallel algorithm showed the greatest cooling energy savings. However, the magnitude of the effect gradually diminished, and it was determined that a balance between the difficulty of maintenance due to the increased number of chillers and optimal cooling energy savings was achieved when using four chillers. In other words, for the weather conditions in Korea and a medium-sized office building, using four chillers with the sequential uniform parallel algorithm resulted in approximately 40% of annual energy and cooling energy savings. The following graph represents the monthly cooling energy consumption for each load distribution algorithm when operating the building with four chillers. It can be observed that during the transitional months of April, May, September, and October, the uniform algorithm consumed the most cooling energy. On the other hand, during the hot months of July and August, the sequential algorithm consumed the highest amount of cooling energy. Throughout the year, the sequential uniform parallel algorithm consumed the least cooling energy. The the following analysis pertains to the operating hours of each chiller. As the simulation was designed to calculate the cooling load in 10-minute intervals, one time step represents 10 minutes. Although the total cooling load remains the same for all algorithms, the uniform algorithm has longer operating hours for chiller 2, 3, and 4 compared to other algorithms. Therefore, it can be inferred that the uniform algorithm operates at lower PLL compared to other algorithms. The optimal algorithm also showed longer annual operating hours for chillers 3 and 4 compared to the other two algorithms. The annual pot load ratio parallel for each of the four chillers when operating with the uniform algorithm is shown in the radial graph. The darker the color, the higher the PLL, indicating higher operating load. In the uniform algorithm, it is observed that all four chillers operate at a PLL of zero point 0.2 or lower for over 20% of the operating time. The annual parallel ratio for each of the four chillers when operating with the sequential algorithm is shown. Similarly, darker colors indicate higher parallel values. In the sequential algorithm, it can be noted that there is significantly less operating time at lower parallel for chillers 2, 3, and 4 compared to the uniform algorithm. The following graph represents the annual parallel ratio for each of the four chillers when operating with the sequential uniform parallel algorithm. It can be observed that this algorithm operates with very high PLL for chiller 2, 3, and 4, unlike the other algorithms. When operating with the optimal algorithm, it is observed that the chillers do not operate solely at high PLL like the sequential uniform PLL algorithm. However, compared to the uniform and sequential algorithms, they operate at low parallel only during specific time periods. Interestingly, chiller 4 operates at low parallel for a significant amount of time. Examining the average coefficient of performance for each chiller in the different algorithms, it can be observed that the sequential uniform parallel algorithm yields the highest average COP for all four chillers. The uniform algorithm has longer operating hours and more time spent at lower parallel for chillers 2, 3, and 4. As a result, chiller 2, 3, and 4 operates at relatively lower efficiency. The sequential algorithm has shorter operating hours for